Good morning and welcome to this webinar on new pathways to CO2 capture. My name is John Favreau from the Horizon Results Booster Initiative, which has organized this webinar together with a group of three Horizon Group projects who are joining forces today to present and discuss with you their results and recommendations. While we're waiting for everybody to enter into the webinar, it does take a while for all the participants to arrive. I can see the numbers ramping up right now. We'd like to discuss a few housekeeping rules to lead us through the webinar. First of all, the webinar is being recorded in its entirety, and we will post a link to the recordings afterwards on the project group members' website. Please don't activate your microphone and videos unless the host gives you permission. We would like to take advantage of all the expertise in the audience today to make this an interactive session. So we welcome questions to the speakers, of course, and you will see a Q&A button on your Zoom window that you can use. And if you can't find it, then go ahead and use the main chat. We do ask you to keep your questions until the question and answer session, because some of your questions might be answered during the talks themselves. We will also be using the Slido tool to conduct a series of polls, a series of live polls to get your feedback. So please participate. It's really easy. And some of you may be familiar with it already. I am now going to put in the chat the link to the Slido poll. 1 second. There you are. You simply, with your browser, you go click on the Slido site, and when you are inside the site, enter the code that you see here, CO2 capture. We will come back to this afterwards, after the presentations when we start to do the live polling, but you might want to get yourself ready already for this. So we have a great list of speakers with us today. I am John Favreau on the right. Our moderators will be Jose Luis Vivente and Vesna Mittelkoop. And we will have 3 speakers, one from each of the projects. And this is the full agenda. You will see that after the projects presentations, we will have a presentation of the policy brief recommendations, followed by the live polling and the Q&A session. So without further ado, I would like to turn over the floor to, I believe it will be Vesna, yes, to give us an introduction from the side of the projects. Vesna, I've heard once in a webinar somebody say, the screen is yours instead of the floor is yours. So please, the screen is yours.
Okay, hello, good morning everyone, and welcome and thank you for turning out in such great numbers. So as John introduced, we gathered here as part of 3 European funded projects. That is CARMOF, member, and More4Air, and we all geared to demonstrate innovative CO2 capture technologies. But that's going to be also in real industrial conditions. What we're going to talk about today is also promising new materials that we are developing for these new generations of CO2 capture technologies, including also utilization storage. And that you will hear in more details, which will follow just in the first 3 talks. So let me introduce first Adolfo Benito from the CARMOF project.
Okay, thank you, Vesna. Thank you very much. Let me to share my presentation. Okay, it's working? Is it working? Okay.
Yes, it's working.
Perfect. Okay, first of all, I am very grateful for this webinar organization. This is an opportunity, a very good opportunity to share all the knowledge related to new technologies for capture CO2, mainly related to high TRLs close to the market and close to the final implementation of the CO2 capture in the industry. And it's important, I think, to share all this kind of information of these new technologies to the people to know exactly what we're doing. Well, in these 10 minutes I have as coordinator of the CARMOF project, I would like to present you the current state of the project and some important issues related to why we are working on this way to improve the current status or solutions related to the CO2 capture. Well, the CARMOF project is a project that begins 4 years ago. That means we are finishing the final solution that we are developing during these 4 years will be finished in August, in the middle of the year, practically. Basically, the title is the following: New process for efficient CO2 capture by innovative adsorption based on modified carbon nanotubes and MOF materials. Well, the main issue related to CARMOF project is that we trust to take the maximum advantage of the hybrid CO2 capture processes. This means that we want to combine different single and well-known CO2 capture technologies in only one capture system to take all the synergetic effects from both technologies, with the idea to reduce energetic expenses of all the processes and to take the best of each single technology. In our case, CARMOF project has been focused on to join two different technologies: a BPCA technology, a vacuum pressure swing adsorption, with a ink-scale membrane system together. To develop the CARMOF project, we made a consortium with 15 partners from 9 countries that involve all the chain value that we want to develop in CARMOF project, because the final product or the final solution that we are developing in CARMOF project is not only the technology, but also to build and to validate a complete pilot plant that will be validated in an end user, in a facilities company. In detail, we are at this point, we are installing and building our pilot plant in a cement plant from Titan company. And this is finally the product that we're developing, a pilot plant related to this hybrid technology or hybrid solution. Our partnership, our consortium is made with expertise in all the chain value of this for develop this this pilot plant, from technological centers and research centers, from manufacturers of materials, absorbent materials, engineering for simulation and for deployment of projects, and finally, of course, end users, companies, where to validate the technology in their own facilities. To introduce a little bit the problem that we are, is you know, everyone knows that one of the most interesting issues that we have as society is to reduce the high levels of contamination or for the emission to avoid all the climate changes problems and issues that we are suffering during the last decades. The processes related to carbon capture and storage tries to capture the CO2 from power plants and industry and to sequester this underground, or maybe we can use this CO2 capture for other purposes. As you know, the single CO2 captures that currently are available in the market has some limitations, mainly related to the ranges of composition of the gas streams. We are a lot of different case studies or cases in the industry with different gas composition, different levels of production of emissions, and not all the single the single technologies that we know are useful for all these cases. This is the main reason why the hybrid processes can give an answer for these limitations of the current single technologies. The hybrid solution is the main approach or the main goal that we are looking for in CARMOF project. Basically, the hybrid solution is to combine different technologies into a hybrid system. This will give us more flexibility and more cost-efficient process, mainly compared with the conventional technologies approaches. In this case, we can see in the diagram in the right side, the different combinations. We have a lot of different combinations that we can do with the different, in 2 and 3 different units with the different traditional technologies. And we can take the best of this combination of technologies to take the maximum advantages of the specific case of the industry in the terms of emissions, in terms of a level of emission and the composition of the gas. In the case of CARMOF project, we are trusting in a process where we combine a membrane system with an absorption, solid absorption system. And basically, this is the general design of the CARMOF approach. The CARMOF is a hybrid system, hybrid solution, based on first a membrane separation unit, together with a second unit that is a vacuum pressure swing absorption unit. The final product that we are developing in CARMOF project is a full demo pilot plant that at this moment is building with a capacity up to 100 tons of CO2 by year. The membrane section, for example, has 2 membrane sections. And for example, the BPCA unit have 3 columns to achieve the final requirements or rate to CO2 purity and output rate that we are expecting. In this case, we combining the both technologies, we expect to achieve a purity higher than 95% of the CO2 with a very high yield. With more detail, the first part of this CARMOF pilot plant is the membrane unit. The membrane unit that now is completely built and validated in a single mode has been designed, constructed, operated, and validated in simulated flue gas, working at 30 cubic meters, normalized cubic meters by hour. I have said before, it's a 2-stage membrane that can produce directly a very pure CO2, 95%. That this 95% of CO2 pure will be mixed finally with the BPCA unit to have a single stream of CO2 pure. For this initial validation in a single mode, we have worked with a synthetic gas with a concentration, a gas stream with a concentration similar to the real case, that is 15% of the CO2 concentration and 2 bars of pressure in the input. And about the BPCA unit, we in the initial, in initial stage, we make a simulation by different software tools of the design and the size of the plant to have the final outputs and the CO2 quality that we are expecting. And we finally design 3 different, for this BPCA unit, 3 different columns working together with a size of 1.5 meters of height. The specific power consumption that we give us in this simulation process with the vacuum pumps was around, or we expect that will be around 150 kilowatts per hour by ton of CO2. And in the right side, we can see the simulation, the process flow diagram and a 3D scheme of the complete BPCA unit with the final dimensions of the complete unit. The core of the BPCA unit is the development of the sorbent materials that we work in this vacuum pressure swing absorption unit. The 3 columns will be fulfilled with the sorbent material, And these sovereign materials has an interesting innovative technology that is columns manufactured by 3D printing technology. With the 3D printing technology, it's a shaping technology that can provide us a very big monoliths to reduce the pressure loss during the operational mode of the unit and to increase the surface contact with the gas stream with the sovereign material. Of course, we have different requirements to develop this material. The first one is that this material can be like a paste, a fluid paste, able to be 3D printed with the typical 3D printing technologies. The second one is in this fluid way or flowable shape of this paste, this can have a CO2 absorption performance according to our expectations. And of course, if we are thinking about to prepare 3 columns with a height of 1.5 meters, we need to have materials and processing and preparation technologies that can, at this moment, work with huge quantities of materials. For example, for a scale up of the pastis productions, we have used a twin screw extruder, a compounder that this is a very easy upscaling technology. Can you see the complete process of fabrication of both of the materials and the 3D print columns in the photographies in the right side? In the up photography, we can see the twin screw extruder that we have used for the scaling of the pastis. We have prepared, or we are preparing more than 900 kilos of 3D printable pastis. And in the bottom, we can see the process of the preparation of this type of columns, of single columns. Previous to this work, we needed to optimize the composition of these pastis in both senses. First, the printability, and the second one, the CO2 absorption performance of these pastis. Finally, after different studies and design experiments, finally, our best samples were a mix of multi-wall carbon nanotubes with polyethylene and more components to achieve the suitable viscosity of the material for the printing process. As you can see in the different diagrams or pictures, you can see we achieve a good uptake. We achieve until 3 nanomoles by gram at 1 bar of pressure. It's an interesting value. And we did some cycles, desorption cycles study, and we see that the stability of the material after multiple cycles was very good. And once we selected this material as our selected material, we go forward to the scale up of the pastis and the 3D printing. The impacts that we want to solve or to achieve with this hybrid solution is, first of all, to increase the competitiveness of the carbon capture and storage solutions, reducing the cost of the CO2 capture and the sustainability of the final products. We are expecting the final calculations relate to the validation of the pilot plant. We are expecting a cost between 40 and 50 euros by ton of the CO2. We want also to increase the durability of the CO2 sorbent materials, reducing the shutdown frequency. This is a problem of the most innovative materials as sorbents, as CO2 sorbents, is the durability and the cyclability of the materials. Of course, to produce a new generation demonstrators based on this hybrid concept, because until now the hybrid concepts are only arrive until simulation or very small laboratory demos, but not at this point. We have not completely developed or deployed a hybrid concept at pilot plant level, deployed in industrial facilities. And we are completely convinced that the hybrid technologies will offer an impressive number of different combination of traditional technologies. And if we have a huge quantity of different combination of traditional technologies, this will allow to treat with an extensive, huge casuistry of gas stream composition and sources that we have in the industry. And we want to explore the maximum possible range of cases in the industry with the hybrid technologies. What is the point? Where are we? We are now in CARMOF project. Well, at this point, the demonstrator with the capacities that we are explaining you is currently built and validated at Camari Titan facilities. You can see a photography of the place we will be installed and validate the final demonstrator. All the equipment and services required for the adaptation of the plant facilities to the installation and operation of the demo unit is doing at this point. Is very important how we will connect the flue gas stream to the CARMOF demonstration unit. And the objectives that we are following in the next month will be to minimize the energy consumption and the CO2 capture by day with a very high purity, a higher of 97%, to evaluate the demonstration performance of this hybrid unit under gas stream composition fluctuations, taking into account that all the simulations that we have did or tests with synthetic gas are done in a fixed gas stream composition of 15% of CO2. But as we know, in this cement industry, we have a strong fluctuation of the gas composition between 10–15% of the CO2. And we need to know how will perform the CARMOF unit, CARMOF demonstrator in this operational mode. And finally, we aim to prepare an instruction manual or guide based on the information collected by the end user partners operating this pilot plant. And that's all. Thank you very much for your time. And it's a pleasure to share with you all the concepts related to the CARMOF project. Thank you very much.
And thank you very much for your presentation, Adolfo. Now we have as our next speaker, we have Emma Paulo. Emma, the floor is yours.
Hi, John. Good morning. I can share my screen?
Yes, indeed.
Can you see it?
Yes, perfect.
Okay. So thank you once again. Thank you, John, for your introduction. My name is Emma Paulo, and I am Applied Research and Development Group Leader in KT Kinetics Technology, and currently I am Innovation Manager for Member Project. Member Project is dealing with advanced membranes and membrane-assisted processes for pre- and post-combustion CO2 capture. Mr. José Luis Viviente is from Tecnalia, is the project coordinator, and the project is started on January 1st of 2018. The aim of the member project is to reduce the cost of the CO2 capture technology through scaling up and advanced manufacturing processes for some key materials that in our project are membranes, catalysts, and sorbents, in order to have the availability of innovative membrane-based technology that can overcome the limitation of the benchmark technology. In our project, we are studying two main applications for these innovative CO2 capture technologies that are CO2 capture in power plants in both pre- and post-combustion operation mode, and in hydrogen generation process with integrated CO2 capture. In the project, we have 17 partners. 6 are coming from research or academic organization, 7 partners from SME, and 4 partners from large industry. In this project, we have identified 3 main steps in order to bring this innovative technology from the starting TRL 4.5 to TRL 6 at the end of the project. The first step is the material production and scale up. The second step is the prototype design and construction. The last step is the demonstration at TRL 6 in the 2 selected applications. The target in terms of performance and cost that we expect to achieve at the end of the project are listed here. We expect to achieve a carbon capture higher than 90% with a reduced CO2 capture cost lower than 30 euro per ton for pre-combustion capture and 40 euro per ton in post-combustion CO2 capture. For the technological route of hydrogen production, we expect still to achieve a CO2 capture higher than 90% with a CO2 capture cost lower than 30 euro per ton. As I said, we are studying 2 main applications of this technology. For the application in power plants, we are using mixed matrix hollow fiber membrane, starting prepared from raw materials, MOF and polymers. In the case of hydrogen production process, we are addressing the innovative technology of the membrane assisted sorption enhanced reforming by using palladium-based membranes and innovative solvents and catalysts. In the upscaling of this technology, as I said, we aim to test the innovative CO2 capture membrane-based technology in 3 prototypes, named the prototype A, B, and C. In prototype A, we will test the pre-combustion CO2 capture by using the mixed matrix membranes. In prototype B, we will test the post-combustion CO2 capture still with the mixed matrix membrane. In prototype C, we will test the pure hydrogen production with integrated CO2 capture with the palladium-based membrane. As a background activity that covers all these technological lines, we are improving, optimizing a specific recycling procedure for the recovery of the critical membrane materials and membrane modules in order to further reduce the cost of the technology. Let's look what we are doing in terms of upscaling for the MMM membrane for pre and post combustion CO2 capture. We have started, as I said, the project at the TRL 4.5, and in terms of material, the metal organic framework zeolite based were available at a scale of around 100 grams. What we have, which is the target of our project, is to bring the manufacturing procedure at the scale of 1 kilogram for each metal organic framework for prototype. And then for the industrial scale production for cost estimation has been considered the range between 10 and 20 tons. In the case of polymers, we are working with polymer PBI and PBACs that are commercial. For the overall membrane module, we have started the project with the availability of a module with a membrane area of 0.1 square meter containing up to 100 hollow fiber. At the end of the project, we expect to achieve a module with a membrane area of around 10 square meter with a number of hollow fiber higher than 10,000 number. And this is considered an industrial process production. Here in this picture, you can see the facility that have been put in place in order to produce the membrane module and to carry out the quality control plan. For the line related to the hydrogen production with integrated CO2 capture, for the sorbent, we have started with, at the beginning of the project, with a material available in a quantity lower than 1 kilogram per day. Now, at the end of the project, we are able to produce this material in the quantity of 50 kilogram per day. For the catalyst, still in this case, we were able to achieve a production at a scale of grams, but at the end of the project now, we are addressing the production of 5 kilogram per batch of catalyst. For the palladium-based membrane, the available technology was able at the beginning of the project to produce membrane with a membrane area of 5 square meters, single membrane per batch. At the end of the project, we are able to produce a membrane module with a membrane area higher than 55 square meter. Still in this case, some picture of sorbent, catalyst, and the palladium-based membranes that we will integrate in our reactor for hydrogen production. As I said, we have 3 prototypes to be tested. Prototype A that will test the pre-combustion capture in power plant with the mixed matrix membrane will be tested at IGEA reforming facility. Prototype B will be tested at a GALP facility in Portugal, and we will test the post-combustion capture in power plant. Prototype C will be tested at the facility of IFE Einor in Norway with the supervision of ZEG Power, and here we will test the pure hydrogen production with the palladium-based membrane. We have several expected impact or anyway key exploitable results that we expect to achieve at the end of the project. They can be divided in 3 main categories. The first one is the process architecture, so the overall process scheme for the pre-combustion CO2 capture based on MMM membrane, post-combustion CO2 capture, and master system for pure hydrogen production. The second category is related to the materials. So we are considering here all the main material that are part of our technology, both in terms of raw material, such as the MOF and polymers, sorbent and catalyst, both in terms of the overall membrane module. And then in the end, we have also another type of exploitable results, that is the service tool. And we have identified, for example, a software tool for the membrane reactor and membrane separation module design, and consulting services for the life cycle analysis of the entire CO2 capture process. Thank you for your attention and for your invitation to be a speaker in this webinar. Thank you.
Thank you very much, Emma, for this talk. Keep in mind that you can be asking questions in the Q&A. Some of you are doing it already. We would like you to continue to do so, and we will get to the questions in the Q&A session. So without further ado, our next speaker will be Guy de Vereld from the University of Mons. So the floor is yours, Guy.
Thanks, John. I will try to share my screen. Do you see my screen?
Not yet.
Not yet?
Now it's coming. And now you're set. We see everything.
Perfect. Sorry for this little delay. Thanks to give me the opportunity to speak about the MOF4R project. MOF4R project is the third project present today. Is focused on adsorption process using metal organic framework, as these materials will be discussed previously, and the adsorption technology also. Just to have a quick idea about the different technology and the different process configuration. Of course, we can imagine pre-combustion, oxy-combustion with oxygen and nitrogen separation, and post-combustion. We see some of them previously. And the technology can be adsorption, cryogenic distillation, membranes, and we can imagine a combination of the process configuration and the separation techniques. In the MOF4R project, we are focused on post-combustion using adsorption technology. And of course, the benchmark technology is absorption in amine solution. Is the only technology at industrial scale. Terrell Knight, but they have some penalty about this technology, some drawback as the sensitivity to the contaminants, the degradation of the solvent, the loss by aerosol, corrosive effect, and so on. And the environmental impact is relatively important. The energy consumption is also a key factor for this. We can imagine and use the benchmark as MEA with high energy consumption, but with mixing solvent or an alternative configuration, we can decrease to 2 gigajoule per ton of CO2 capture. We can't imagine to reach lower energy consumption in some other project as the 3D mix project at Dunkerque using mixed solvent. The idea by adsorption is to use a well-known separation process with non-toxic element, and of course to see the suitable for the various operating conditions. And the idea of MOF4R project is to test this adsorption technology in the different case with different CO2 concentration, with different impurity. The MOF4R project is project start 2.5 years ago with 30 partners, 8 countries, and the budget is around 11 millions of euros. The idea of the project, as the 2 other projects, is of course decrease the cost of capture and CO2 capture and sequestration or using, and to this, to improve the performance of the materials, and we focus on metal organic frameworks, to fine-tune the materials for the application, and also to improve the design of the process to reach the objective. Of course, we need to test this material at in the real industrial condition. And of course, as other projects, we have communication part and also dissemination and life cycle assessment in the project. The idea is to also replicate the technology. If we can summarize, we have 2 main objectives: to improve the adsorption capture process with 2 different technologies. I give some information in the next slide, and to improve the efficiency of the MOF for the application. The MOF, just to have a quick overview, is an hybrid porous solids. We say generally new class of crystallized porous material, but the new class, the beginning start 25 years ago, is not really new, but for the adsorption application, it's really new. And the idea is to take into account all aspects to capture CO2 and design the materials to have the adequate property and to be stable, to be in various conditions, to limit the effect of impurity and so on. And we can play on the sides of the porous channel, and we can also work on the chemical function put on the organic ligand, because it's an hybrid solid with inorganic part and organic part. The target for the MOF is to have a good working capacity in average flue gas condition, a good selectivity, good stability with water and acid gas, and also to stay below 50 kilojoule per mole for the regionability, to minimize the energy consumption for this step. We can imagine two different technologies to regenerate the material after adsorption, because it's a batch process. We can imagine to increase the temperature. We can see in the example the increase of the temperature, and we can use, in this case, waste heat. The problem of this technology is the long time for heating and cooling, and we need a high amount of adsorbent. The second one is the pressure swing adsorption, but we can also say vacuum swing adsorption. It depends the desorption pressure in the cycle. It's a rapid cycle with less investment cost, but of course we need to have a lot of mechanic energy requirement. Okay, the idea is to test this technology with flue gas with a large range of CO2 concentration between 5 and 33%. We can see the principle of the two technology. One is testing the MOF for air project in the thermal swing adsorption, but it's an original configuration because we put in, we cycle the solid in the adsorption reactor and desorption reactor to improve the heat transfer and decrease the time to perform it. And we use vacuum pressure swing absorption with different configuration, 2 column, 3 column, 4 column, will be tested in the process. Just to be clear, this configuration we will test at TRL 5 with some kilo of adsorbent, and we will treat some cubic normometer cube per hour of the flue gas. And we decide to design and build 3 pilot units of pressure vacuum swing absorption unit, just to show you in this pilot, we take into account all steps to the purification process. It's just a rough design of the unit, and you can see in this design three columns as more or less than Adolfo say in the first presentation. Of course, this presentation will be completely different because we work with pellets inside the columns. To have an idea, the columns, the volume of the columns is around 40 liters, and we will work in one pilot plant with 60, 70 kilos of CARMOF. We will test this pilot on 3 different sites, one in Norway, in Mondstadt, another in Tupras in Turkey, and the last one in Solamat in France. We test for the raffinery and power plant. We test also for the chemical company and for the waste, industrial waste incinerator, to have a large overview of flue gas treated. The impact of the project, as said previously, we need to improve the MOF performance, and especially to be able to produce at large scale, as say in the previous presentation. It's important to produce. The objective is to produce the CARMOF at the scale of 150 kilograms, and to increase the performance of the cycle. You can see the objective in terms of energy consumption and in terms of cost. The idea is to reach below 2 gigajoules per ton of CO2. We have an industrial cluster board. I take the opportunity to say, if you have some interest to be included in your industrial cluster board, don't hesitate to contact me. Another important point is to develop MOF technology in Europe. Okay, in this project, we will focus on the complaint change with the pre-treatment of the flue gas, the CO2 capture unit, but also take into account the use of the CO2, and take into account, if possible, if it's possible to integrate different operating units. Thanks for your kind attention, and don't hesitate to contact me if you want more information.
And thank you very much for this presentation, Guy, and we look forward to also getting questions also for you after this. So this concludes the, let's call it the technical part of the webinar, the technical presentations in the webinar. Another very important purpose of this webinar, and the purpose for which the project group came together, was also to write a series of recommendations targeted at policymakers, those who are making policy, in particular in the European Commission. And they have written a set of recommendations that they would like now to present to you, and also receive some feedback from you on this. So at this point, I would like to pass the floor to Vesna and to Jose Luis, who are going to, perhaps it will just be Vesna, but in any case, a presentation by them on the recommendations they have produced for discussion then.
I'm trying to share my screen. Can you see it already?
Yes, I can see it. Yes, all clear.
Right. Okay. I mean, as John introduced, we put together a number of policy recommendations. We'll address each one of them, and we'll go through one by one. So it will take some time. So we'll do that interchangeably, myself and Jose Luis. So basically, I will start with what we set as a policy recommendation number one. That one deals with provisions which are needed for key technological advancement and enhancing the future roadmap for CO2 capture technologies. So basically, this one is addressing that any technology development is needed for specific industrial applications. So industrial sites can be different, so it varies from industrial facility to another. So as such, the technology developed in those specific sites is reliant on accessibility to clean, sustainable energy sources. That's like energy aspect to powering basically any installation specific industrial source. And that also requires the need for heat integration at the plant side. So as such, these technological advancements can be only achieved through process intensification and modularization and scalability of building such plants. Alongside that comes also cost effectiveness and scalability of the materials themselves, because they eventually get into the bill, and in such way we can reduce the cost and energy demand of the entire CO2 capture process and process intensification. So in this respect, it will be beneficial if policymakers could promote these technological advancements. And one of the means that we could identify ourselves is through including support for them in the forthcoming calls at European Research Roadmap. So,
it's my time.
Yeah.
Yes, I'm here. Yeah, I used to talk about the second recommendation is related to provide support to increase the manufacturing readiness level of the CCUS industry. We have to think that while the technology readiness level is used to assess the maturity of technology, it does not address the manufacturing maturity of key materials and components that are the main basis of the technology. And so we have to think that the manufacturing readiness and producibility are as important to the successful development of a system as the technology used in the system. So we have to look both the technology readiness level and the manufacturing readiness level. And it is necessary to support the improvement of the manufacturing readiness level to increase to grow, as we see in the previous project. We're talking about moving from grams to kilograms and to tons at the end, because if we want to go to the market and have a large replication of the technology, you have to have a big supply of the materials you use to develop this technology, the materials and components, I would say. And this is the only way where you can replicate and you can go to the market and have a large impact. And also, in some cases, because the CO2 emission is in a large amount, and you need also large amount of materials to deal with, because in this way we can tackle different CO2 emission sources with different, as we go to the power supply, common heat and power, we have steel making companies, we have large emission, but we also have, let's put a smaller between brackets, like biogas, biogas, where you have a smaller CO2 emission than in steel making industries or other large CO2 emission industries. So we also need to support the manufacturing readiness level of all these materials and components.
Okay, I'll take the next one.
Yes.
So yeah, the next one we would like to address is the need for providing financial support, obviously, for the formation of industrial clusters. That's something that you've been probably witnessing in the last year or two. At present, there's certain means for supporting industrial clusters, and that can be at national, local, and EU levels. One such example is Northern Light project and Porthos. But still, these industrial clusters are still in their early days, and such initiatives still would need a large governmental backed loans or boosters, or even grants for developing and supersizing this kind of CO2 transport storage hubs and entire infrastructure, because as such at present these funds are still insufficient, and there is a create cost revenue gap which we try to bridge in our projects, but such help is much needed, and this has to be addressed if we want to move on towards the full scale of finding solutions to basically this global challenge. We could identify one such support channel, which could potentially be through the EU Innovation Fund. But at the moment, EU Innovation Fund, as some of you may know with experience, is oversubscribed a factor, I think, about 10 to 20 times. The next one we'll look at is.
Yes, and the recommendation number 4 is related to the support of the CCUS through regulatory and strategic policy. This is already ongoing because we have a push for capture technology, because there is a cost for the industry due to the taxes for the CO2 emissions. But this should be improved and to be continually put in place. And I think we need an adjustment of the regulatory context, because it's important to frame the development of the CCUS technologies and infrastructures in the coming years, and with the purpose of removing barriers to the role of the CCUS that can play in the CO2 emission mitigation. So the point is to, as mainly an European level, that we have a European policy, but we have to match the carbon capture, transport, and storage strategy and policy at the European level with the member state policy. And this involves incentives for proactive development of strategic CO2 transports and storage infrastructure and solution with different ways of transport, and also increase infrastructure capabilities for this CO2 transport, and to facilitate the access to this infrastructure for raw materials and to the markets for end user products. So decreasing the additional CO2 emission due to the transportation. And also we are talking here about regulatory instruments such as the carbon taxation on both direct and indirect emissions that should be explored to help to make CCUS more competitive. As well is we think, yeah, this is from my side, is you think that you import materials from other countries that don't have CO2 taxation might be the cost, how to deal with this, for instance. So that's, and you produce a higher cost in Europe. There's because you have taxation in CO2 capture. So this is also should be looked at.
And the last one we identify is basically to boost the social acceptance of CCUS technologies, because engaging local communities can be seen as a crucial pathway to developing, especially then adopting CCUS solutions, and as such can be really a rewarding experience. So we've noticed ourselves that we tried coming up with a number of solutions for doing so in our proposals, typically, where overall public engagement activities can be seen as a bit challenging aspect of such one project or in general policy development. But still, there are a number of means and instruments that this can be done in such way that, for example, there should be some public consultations or making local groups which will be interacting with authorities or maybe with researchers or industrial parties. And of course, for such thing, we also need additional financial support because, you know, public awareness raising activities can be very engaging and can be also on different spots, and can be also requiring not that much funding as, of course, building the infrastructure, but it can contribute to the overall awareness level raising. So one of other means would be what we thought of as public debate forums, where discussion can be led on European strategies for CCUS, and that can be done at the local level, national level, online, globally, so in different means. So basically, yeah, we're thinking of boosting the way the local communities can empower themselves to just increase their participation. Not only in, that's also one of the aspects of technical specifications, to get them familiar with the type of technology we're developing, but also just to engage them in overall issues which are critical to adopting such technologies, such as gas leakage or any other environmental impacts that specific technology can create. So that's now our number 5, and we try to summarize our recommendations in such a way. We are happy to take more questions on this or suggestions.
Okay, well, thank you very much, Vesna and Jose Luis. In fact, the intention now is to begin to get your feedback on especially on these recommendations, and of course on everything else that we have heard during the webinar. So at this point, we are now going to pass over into the session on a live polling where we can begin to get feedback from you. So if you can, yes, unshare your screen, and Julie will now begin to share her screen. I have put into the chat the link to the Slido tool on that you can click on in your browser. Click on CO2 capture. Click onto it. That is right in the CO2 capture. I'll do the same now on my own browser so that I can participate along with you. So everybody go to Slido and put in CO2 capture and begin to put in exactly what we're seeing here. And you can see live the responses of the people who are, let me put in my own response. So as you can see, we are building up a set of reactions. Okay. Keep your responses coming. If you want to do more than one, go ahead. All right, I see that cost is remaining as a big one. Social acceptance is becoming an important one. Funding, yes, cost and funding are essentially the same. Let's keep building up a good set of responses that people that they can feed into their. This will help them to prioritize their recommendations. It's very interesting for them, and for us, I actually think it's rather fun. Okay, you can see we're building up a broad series of responses, of which cost and social acceptance, some politics at the center. Yes. Okay, it looks like we're beginning to stabilize here. Yes. No, more are arriving now. Many of them have to do essentially with high cost, price, so they're coming together. There is some, I would say at the second level, what we're seeing is politics and social acceptance. Yes. And again, some there are a couple of responses that involve the need for novel methods also. So we're happy to see that, because some of the recommendations also have to do with that. Experience also, this is going to be an important factor also that we also believe this very much too. Okay, let's give it a few more seconds so we can get everything in there. Legislation, we're very happy to see that mentioned in there. because that is one of the recommendations. Availability of energy, extremely interesting, that one. Very nice. Negative emissions, another one important. Storage capacity is going to be something that we also agree this is going to be an issue. Plus common strategy. Very welcome to see that, because that is in fact one of the purposes of this group coming together to try to recommend a common strategy. Okay, I think at this point we have a relatively stable feedback. So let's move on to the second question in the poll. So, and the second question is, what would you consider to be the two main barriers? So select that to the successful deployment of CCUS. So this is a chance to get an idea of how the audience sees what they seem to be really in sense of priorities. Okay, so we're seeing that incentives right now is leading the way, which I find to be very interesting. Now we're building up. It remains to be incentives so far, but we're beginning to see some of the other ones happening too. Let me put in my opinion. Okay, I have added my own opinion. Okay, so low incentives. So we're very happy to see that response, because one of the thrusts of the set of recommendations is indeed to that policymakers can put out incentives of various types. We had a lot of discussions about where the incentives should be, and you will see that in the way that the recommendations have been put together. Okay, thank you very much. I see that we have low incentives as being number one, and then regulation and technical aspects being next in line for this. And this will help us to fine tune the recommendations that are being done, that are being put together when they go into their final form in the policy brief. So let's go on to the third question now. And now we're moving towards technological advances. What are we going to need to drive the technological advancements in the future roadmap? So is it going to be demonstrations? Do we need more research? What is needed? So I'll put in my opinion. All right. I see that an early lead has been taken by large-scale demonstrations, which is certainly not a surprise, because there's still much to learn about the demonstrations. Long-term validation of the technology, together with ensuring the value chain. I think, as I recall, this has a lot to do with the second recommendation, which had to do with making sure that the manufacturing industry was up to scale, was up to market readiness for this. So it's good to see a validation of that. I think we have stabilized now on this poll question. So let's move on to the fourth poll question. So now we move more to the area of the recommendation, which was about having to do with regulation incentives. We mentioned a few. Which do you think are the ones that are important to be implemented or improved to support CCUS? Is it the carbon tax? Is it something else? I'll put in my opinion. All right, we seem to have a clear leader here, which is, yes, incentives for using them. The captured CO2 products and carbon removal, including a CO tax on products. Okay, and then there's also a carbon tax on emissions. But then the main one, we can see this pretty clearly, is the first one. Okay, very good. Thank you very much. It looks like we have stabilized here. So let's move on now to the last question. Now, can you prioritize? Now, what will happen is when you select one, it will give you a number. You will see a number. So this is how you will be able to set up your priorities from 1 to 3 on these 3 areas that you consider to be a priority for financial support. So when you click on the circle, you will see a number appear in the circle. So click on the first one first that you consider to be number 1, and then consider the one you to be number 2, and it will provide you with the numbers. And we will have a way of seeing how you prioritize these. I'll give you a minute or two to do it. If you feel like you did it wrong and you need to do it again, then you can unclick all of them and start over again. But right now, it looks like we have, frankly, it looks like everybody is, they are considered almost to be of equal priority. There is a slight lead on about capture technology and development. And the problem right after that is the problem of transport, especially cross-border transport and the storage infrastructure. And the clusters is considered to be at the lowest level of priority, but not by much. I think the message that I'm seeing from this is that all of them are considered to be relatively important. Okay, so thank you very much. I believe we now have a set of good poll answers, and these will also be provided as part of the results of the webinar. So with this, we move into a general Q&A session. We would like to hear from you. We do have some a number of questions now in the Q&A chat. Some of them are from each of you. So please, all of you on our panel today, turn on your videos and be prepared to answer questions that have come in. So let's select. Some of the questions have already been answered online. So let's get to some of the questions that have not yet been answered. So I'm now confused. I'm not sure exactly which ones have been answered and which ones have not. Julie, can you give me an idea about which ones are still to be answered? Let's see. I think we have one. Open questions remain. There is one for, I believe it will be for Guy. So you can see 2 GI times CO2 in terms of thermal electric energy. In case both, shall you evaluate the amount of energy from?
Yes, clearly it's a thermal energy. Of course, it's always complicated to compare thermal energy or to compare thermal energy and electric energy. We use this value with European mix of electricity production. This depends, of course, but it's primary energy to use to produce electricity.
Okay, thank you very much. We also have another question that has arrived also from Fabio Canizzaro. Have you tested the material stability properties in high temperature conditions, about 300 degrees C? I don't remember exactly who this is directed at, but who can
I think it's not for MOF4R project because I start my presentation after this.
Yeah, I believe it was Emma, perhaps.
Yes, John, I believe it's for me.
Yes.
For the MMM membranes, this type of membrane are low temperature membrane, let's say, so are suitable for operation at low temperature, but anyway, not exceeding 250 degrees C. In the case of palladium-based membrane, in this case, these are high temperature membrane. And yes, indeed, we will test the stability of this membrane at a temperature close to 500 degrees C. In all prototypes, anyway, we will test the stability of the membrane. This is one of the main key objective of the project.
Okay, thank you very much. Now, we have a series of questions here that I believe some of them arrived very early for, I believe it was Adolfo. And I think they're intended to be, correct me if I'm wrong, I believe they were intended to be answered live. Let me see which ones have already been answered or not. In that case, I will go back to the questions that are there now. What technology will be leading considering 2050 net zero targets? I'm going to open this up to whoever would like to answer in the panel. Does somebody in the panel have an opinion on this? Guy, what are your thoughts on this?
It's a good question.
Putting you
my opinion, perhaps a combination of different technology as present today, adsorption technology or membrane technology could be relatively interesting. But we need to improve the capacity of the technology, because for the moment the unit to capture CO2 by adsorption or by membrane is huge compared to the amine solution. Yes. But for the moment, we can imagine the technology at middle level. It's difficult to imagine technology at very low level to see it's possible to reach industrial level in 30 years.
All right, thanks very much.
Just to say, I think, in my point of view, it will be complicated to reach net zero inside the process. It will be complicated to do it without CO2 emission.
I understand. Thank you very much. Adolfo, I see that you would like to make.
Yes, thank you. Regarding to this, I think to think in a leading technology in the future, in the 2050, is so difficult at this moment to think about. But I trust on the combination of different technologies, maybe membranes with amines, maybe membranes with solid sorbents, membranes with cryogenic solutions. We don't know, or more than two combination of technologies adapted or fitted to different cases studies. At this moment, my opinion is that, for example, in the membranes, we have a huge field for evolution of the membranes technology in the future. Maybe we reach in the future a top on the improvement of the membranes performance. We don't know, or maybe if in the future the membranes will be very competitive, will be the first option. We don't know. But at this moment, my opinion is try to combine different solutions to improve.
All right, thank you very much for this comment. Would any of the other panelists would like to comment on this very important questions? Maybe I'd like to follow up that question to a question with a question that was received by Adolfo originally, and which you privately responded to, but I think it's important enough that others can also hear your response, Adolfo, to this. And this is, what about the final price of the CO2 capture? Is it really economically feasible, not just technologically feasible? The carbon nanotubes are expensive and its production is very energy consumptive. So can you expand on your reply to how you expect to handle these very possible high prices of production? You are muted, Adolfo, if you were responding.
Sorry. Sorry, I didn't hear the last. Can you repeat, John?
Oh, yes. You received a question earlier, which I believe you responded
Okay.
to, but I think
No
it
problem.
was to,
I can answer later. No. Yeah,
everybody.
perfectly. Yes. Well, I know. The good thing about the price of the CO2 capture, of course, in the case this question, Mr. Nisami is asking about the high price of the MOF or the carbon nanotubes. The question for example, in CARMOF project is that the most innovative solution that we are giving in the market is the hybrid, the combination. The good thing that we have in CARMOF project is that in future iterations, we can change easily the nature of the sorbent material or the nature of the membranes unit. This means that with the same base, we can add improvements in iteration flow to have each time reductions and reduction on the final price of the CO2 capture process. This is the idea. Maybe the use of carbon nanotubes in combination with polyethylene is not the best solution in the future for this kind of solution, but has been very useful for us to see the limitations of these materials in a hybrid solution. But maybe only changing the columns that we are working on with other type of solvents, the price and the energy expenses must decrease a lot. This is how I am thinking now. We are thinking at this moment more in the technologies than in the final materials of this the combination.
Yes, a comment on what you said, but from Michael that just came in and says that in any case, you do have to compare with the huge cost of the classic dilution ventilation. Fine. Another rather provocative question has arrived that I would be interested in seeing those of you in the projects responding to from Alex.
John,
yes.
Sorry, may I comment something on the previous
Oh,
remark
course,
on the
yes.
cost?
By
Yes.
all means, yes.
Yeah, that's it's at least in the member project, we are doing life cycle analysis and life cost analysis, taking the whole chain from the raw material extraction and to the recycling. So we have all the whole chain, and we can identify, and we see there are 5 impacts. One of the CO2 emissions, impact on human health, and so on. There are different impacts, and you can identify in each prototype which will be in the main material or step producing the highest impact in this towards this when you look for this life cycle analysis, and also in the cost. It's all related, and you compare also with the benchmark technologies. And also I have to point out that the idea of increasing the production of the materials, they not only increase the production of the material, they also look for more environmental friendly fabrication processes. So I know in our case, they have reduced by 2 orders the amount of solvents to produce the MOF, one of the MOF. And they have reduced by 7 the cost of the MOF. So there's still room, and they work on this to have a low impact, let's put in general, and in the production, and also reducing the cost of the materials. So, and this is taken into account also when we do the life cycle cost analysis, and also when they provide cost when scaling up the production to the tons scale we were talking before. So, and we have to think that, okay, they produce MOF here for mixed matrix membranes, but the MOF itself can be used also as a standalone product. That's why they are thinking in ton scales production as well, because it's not only for our application, they can be used as a sorbent, as we can see in other projects. So this there are technologies that can be used in a different way. In the mixed matrix, you add the MOF in a small amount, in fact, for the membranes to increase the properties of permeation and selectivity, or selectivity. But the same MOF not deal in the project because we don't address this, can be also studied in other application directly as a solvent. But it's, you cannot have big projects, so you have to focus on how. But that's why we also remind the partners that they have to look on their own product and see if there are other exploitable routes that where this product can be used, not only in our prototypes. They can be used, the catalyst or the solvent can be used in something that has reforming, or in other application where the catalyst is also suitable for. So we have to we push, and I think they also think in this way. The industrial partners. In our case, we have industries supporting all the raw materials production. So that's, and we have asked them to do this upscaling. So this, and I think they know more than us in their own field. They're working, and I'm sure they know also what could be the industrialization besides the exact application they're working in the project. You know, that's something to also consider.
All right,
I think
Guy?
maybe also replying to Alex, was Alex, I saw a question about
Yes, exactly.
industry, is
Are
it
they
committed
committing?
to, yeah, somehow I also replying to this.
All right, good. Guy, you had a comment I see to make.
Yes, it's difficult to say no, because we are always in the development phase, and for the MOF, as José Luis say, we decrease clearly the environmental impact by using water and solvent. Previously, we use organic solvent and so on. We need also to decrease the price. For the MOF, the price could be very different. We can imagine a factor between 1 and 100. It depends the availability of the organic ligand and so on. In the project, I see a long question about the lake information about MOF and so on. Of course, is the heart of the project. We are in the middle of the project, and we have clearly select some material, identify some material with some of them we imagine to patent it, but we imagine we have a material with 10% or 20% of lower property, but the price is more or less 10 times cheap, and we need to manage this different feeling for the future. We need to continue to improve the technology to the next step, and probably for the membrane and for the adsorbent or as MOF, the main step is to be able to produce at a very large scale in low cost the material with the same properties.
Thank you very much for this, Guy. If any other members of the panel would like to make a final comment on this, please step forward. Otherwise, we have reached the end of the webinar. We want to respect your needs to go on to your next meetings or whatever. It has been a very valuable webinar for us, and I certainly hope that it has been a valuable webinar for you. You will indeed receive both the recording and all of the presentations. They will be made available. There was a question about this. And in fact, we will ensure that the chat is saved, and that any questions that came in the chat and were not yet answered, we will get back to you. By all means, feel free to join to contact the members of the project group. I saw at least one question even asking about the possibility to add another pilot plant. So we're very happy to see that we've managed to connect people together on this. Other than that, I and we wish you all the best for the remainder of the day, and we look forward to being in contact with you one way or another sometime in the future. Goodbye, and thank you very much to all.
Bye.
Bye bye. Thank